Afternoon all. Here's the circuit, the StepCounter circuit, whose output emulates the Hall effect feedback of the original stepper motor. Here's the PIC 16F84A. Here's an input optocoupler. Now I've since changed this, and I'll explain why in a minute. Here's the output optocoupler, an H11G3, has Darlington Output, that the original drive stepper motor had a Darlington Output. And so I wanted to recreate that output right there. Now, the input optocoupler, the problem I had was, as this sits, it would work, but when I joined this input to the step input of the drive stepper motor, the drive stepper motor would not work. So I had to separate these two connections right here, one for the step input to the microcontroller and one for the step input to the drive stepper motor. Let me put this up right here. We'll take a look at the way the circuit sits right now. You can see that I have two optocouplers. One for the PIC 16F84A input, that's the step input, and one for the step input of the drive stepper motor. Both input LEDs have 24 volt pull-up resistors right here on the anode side. They're 1 kilo ohm, 1 watt, and they're on the anode side of the input LEDs. The cathode side of the input LEDs are tied together, and they are stepped with a 24 volt step frequency. And both outputs have different pull-up voltages right here also. So the PIC 16F84A has a 220 ohm 5 volt connection right here, and the drive stepper motor required a 24 volt pull-up resistor right here in the collector of the photo transistor. So here, the clock frequency, the step frequency, is 5 volts to ground, and here the step input to the drive stepper motor is 24 volts to ground. That worked out really nice. I like that a lot better than trying to tie this point right here to this point right here. The stepper motor would not work. Now, the PIC 16F84, the clock frequency, the step frequency into it worked, but this part down here didn't when I connected the step input to that point right there. But by putting the optocoupler in here, I separated both circuits. Nice. That worked out really well. Now, in order to get this circuit in the confined area that I was required to put it in, I had to change this IC right here. I went away from the PIC 16F84A, which has 18 pins, to a PIC 12F615, which has 8 pins. And you'll notice down here that I had to use an external oscillator for this IC, but with the PIC 12F615, it has an option for an internal oscillator, which we could do away with that right there and save even more space on the board. Let me put that circuit up. this right here is the final circuit. Let's get a little bit closer. Now here is the final circuit using the PIC 12F615. It has 1, 2, 3, 4, 5, 6 general purpose I/O. I'm using pin 7 GP0 as an input. That's the step input to the PIC 12F615. GP1 is the emulated Hall effect output. So we have an input here and an output here, pin 7 and pin 6. The output is connected to the cathode of this input LED of the H11G3. And the anode is tied up to 5 volts DC through a current limiting 180 ohm resistor. The output, the Darlington output, I don't have it drawn as a Darlington output, but this is a Darlington output. The collector tied to a 100 ohm quarter watt resistor going back to the machine, and the emitter going back to the machine. On the input side, we have 2 optocouplers. Let me draw the little arrows there indicating photons driving into the base of the phototransistor. I left those out, sorry about that. So we have one step input from the machine that used to go directly to the original drive/stepper motor and run that stepper motor, whose Hall effect feedback would go back to the machine. But we can't get that drive stepper motor no more. So I had to create this circuit right here. What do you mean we, people? You got a frog in your pocket? Ain't no we here. Okay. So here the machine has a step input that used to go to the original drive/stepper motor. And I've got 2 optocouplers. One takes that step input and takes it into the microcontroller input. The other optocoupler takes it into the drive stepper motor step input to make the motor rotate. So here we have plus 24 volts DC. This is the machine step circuit is based on plus 24 volts DC to ground. On the anode side of each input optocoupler, we have a current limiting resistor of 1 kilo ohm up to plus 24 volts DC on both input LEDs. The step input is tied to the cathode of those input LEDs. Now when the step input is high, each LED is off and no photons are transmitted to the base of those transistors right there. When the step is low, when the step input is low, current flows from plus 24 volts DC through the current limiting resistor back to the source, the driven source of that step circuit. Same down here because they're tied together. And photons are emitted into the bases of those phototransistors, and the phototransistors are turned on So you have a low right here. This point goes low. At this point goes low. So here we have a low and a low. When the input LEDs are off, this point right here goes high through the pull-up resistor up to 5 volts. And this point right here goes high up to plus 24 volts. Isn't that amazing? That is amazing. All right. Now, the circuit takes 100 step inputs and converts that to 1 on-off here at the output. So for 50 steps, the output is high, and this input LED would be off because we'd have 5 volts here and 5 volts here. The input LED would be off. And for the next 50 steps, the output would be low. And so we have a low here, current would flow through here, and the input LED would be turned on. I like that. You know, you get something in your mind and you say, I'm going to do it this way, and it's so much fun to invent. I want y'all to go out there and make something. Oh, one more thing. Down here we have a direction input to the drive/stepper motor, and that comes from the machine also. So we have machine input here for step, machine input for direction, and that makes the motor run clockwise or counterclockwise. And we have our Hall effect output, our emulated Hall effect feedback output back to the machine. All right. Okay. Now I've got the circuit board built, and I think I'll put a couple of pictures and whatnot up at the end of this video so you can see that circuit board, this final circuit right here. One of the nice things about using this PIC 16, or I'm sorry, PIC 12F615, was that the PIC 16F84A was an 18-pin device. This right here is an 8-pin device, so that cut down on the footprint on the circuit board. And I could set this circuit right here. Notice there's no clock or crystal. I could set this PIC 12F615 to use an internal oscillator. So that reduced the circuit board's footprint. Nice. I like that. I like that right there. Now this is a very versatile IC. It has, you can, there's some analog inputs and other things that you can use inside this IC right here, depending on how you set it up. Oh, that's another thing. I had to make some changes to the code to convert my code from PIC 16F84A to PIC 12F615. I'm going to have to put that up so that you can see what changes were made. I'll do that in the next video. All right, folks. Thank you very much for stopping by. I always enjoy it when you come over to see what we're doing. It's very nice. Very nice when something can fall out of my mind into the real world. Good night, folks. We'll see you next time.